Hello, everyone. Good afternoon. First of all, I would like to thank you all for registering and taking time out on a Sunday to learn about PSVMS Pressure Safety Valve Management System in accordance with API 527 and API 576 by using VAIL-Plant PSVMS module. My name is Aisha Khalik and I would be your introductory speaker for today. It's our pleasure to host an international audience and to host this webinar for international audience like you. This is our 106th webinar in the series of technical webinars that we are conducting every month. As a practice, we are conducting one webinar each month. So please follow us on LinkedIn and YouTube and make sure to check our website for the latest updates as well. So today, like always, I am with an experienced panel of speakers. I have my colleague, Mr. Ijazul Karim Rao, who's Managing Director, Principal Integrity and Safety Consultant. Madam Mubina Khatun, she's Director, Engineering Services at Velosi, and Mr. Anthony James William, who's General Manager for Global Sales. Moving forward during this webinar, we encourage you to keep asking questions to clear any doubts. We would definitely like your engagement on this topic. You can type your questions in the question answer window and you will receive a response from our team, or your question might be taken live during the session. We will try to answer questions as much as possible during this session, but as we will also have a detailed question and answer session after the completion of the topic, please accept our apologies if your questions remain unanswered, because we have to be selective due to the large number of questions we generally receive. So furthermore, we will also be issuing participation certificates to all those who have attended at least 80% of the webinar and have participated in the discussion through question and answers. Before we begin, although most of us are in the comfort zone of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of everyone, of ourselves and those who are around us. Since this is a quite technical subject, we will touch only the key theoretical and practical aspects of PSVMS in accordance with API 527 and API 576 by using VAIL-Plant PSVMS module. So coming towards Velosi introduction, I would like to tell you about ourselves, what we do, and what are our what are the businesses that we are indulged in. So Velosi is a leading global consultancy firm that provides asset integrity management, HSE, engineering, environmental, and software solutions to clients in the oil and gas, energy, power, and petrochemical industries around the world. We also have our in-house proprietary software VAIL-Plant, which is an industry-leading SAP-certified complete asset integrity solution currently being used by oil and gas giants such as ADNOC, Dragon Oil, TANAP, and many more. Founded in 1982 in Malaysia, Velosi Group was then acquired by Apple Spain in 2011. Right now, we operate globally, and we have our footprints in more than 86 countries with an industry experience of more than 44 years. We have so far completed around 1,500 projects with 550 plus satisfied clients around the world. Our areas of expertise include, but not limited to, asset integrity management services, HSE and environmental services, engineering services, AI and software services, and training services.
Assalamu alaikum and good day, everyone. So coming to the topic. So today's topic is PSVs and PRVs. How they should be managed. So the first, what are PSVs and PRVs? PSV is a pressure safety valve and PRV is a pressure relief valve. So as a definition point of view, if we start like as the academic, and as a academic, like a basic knowledge is there. So the objective or attendees where I'm addressing from a young university graduate to the experienced people. So there would be some basic things. So I hope you will not feel like why so basic things are being discussed. But anyway, we are discussing the basic aspects of the PSV rather than how PSVs should be managed. So here, if we see pressure safety valve, basically is required for the gases and steam or vapors, whereas pressure relief valve normally for the liquid service or wet water. Now, both PSVs and PRVs are installed for the protection of the equipment, high pressure equipment or medium pressure equipment or low pressure equipment. If system pressure increase more than design limit of that particular equipment, rather than equipment should be busting, the PSV should pop up. That is the purpose of the PSVs. Like if a pressure vessel is designed, let's say for 100 bar, and outlet of that pressure vessel is closed due to some reason, or there could be some heat effects coming from externally due to some reasons. So in that scenario, pressure may increase for the system. So if pressure for the system would be increasing, then it may lead to the burst or failure of that particular mechanical equipment or mechanical system. So to avoid that scenario, the PSVs and PRVs are installed, or not both, because for the liquid service, a PRV would be installed, and for uh, gas service or vapor service, PSV would be installed, and there would be a set point for these PSVs, and as the set point would be crossed, the PSV or PRV will lift and extra pressure can be released. So in general, set point generally is 10%. So, but my reference is telling that for the gas service, the range of 3% plus, or for liquid service, range of 10% above the working pressure or design pressure is generally allowed. So in general, PRVs open gradually, whereas for the gas service, PSVs open as a pop-up or sudden opening. So a function both emergency relief and pressure regulation or system stabilization. This is the purpose. Basically, like what is the purpose? Why they are installed? Number one, prevent explosions, protect expensive equipment. They should not burst due to high pressure. Personal safety, because if equipment will burst, then it may cause explosion. Regulatory compliance and operational stability. So both, like to protect high, like a PSV, PRV, same high risk environment like steam boilers, gas storage tanks, vessels, chemical reactors where immediate pressure release is critical. Whereas PRVs for liquid system, for HVAC system, for water distribution pipelines and home water heaters, the PRVs are applied. Now, if we try to see the components of the PSVs, here, this is the spring and valve body, disc, adjusting ring, and the nozzle from where the below it is the pressure vessel. So, body, nozzle, disc, spring, and how it works, system pressure increase. When the pressure exceeds set pressure, spring force is overcome, then disc lifts and excess fluid discharge to the relief system. Pressure reduced, valve resets or reseats. Like a kettle, release steam to prevent explosion, just like that. Now, why pressure safety valves are critical? Problem is like if there is a high pressure in an equipment or high pressurized system, so it may burst. There could be explosion. So prevent catastrophic vessel rupture. Protect, because if there would be explosion or rupture, then it can impact the environment or the people around it. Then it also helps to safeguard costly equipment because it should not fail or rupture. Then there is also mandatory API 5, like 20, API 521 or ASME 8 mandatory requirement. Choosing the right PSV, consider fluid type, gas, vapor, or liquid, operating temperature, pressure range. Then, like a proper sizing is critical because undersize may lead to insufficient relief, oversize, frequent lifting, and reduce lifespan. This is general. Now, if we try to see in the overall layer of protection analysis where PSVs comes, there are altogether 9 layers of protection in any process plant, ideal process plant, I would say. It says the first is like a inherent safe design or process design, where the equipments are designed to their codes and standards material of construction is selected properly, the equipment sizes are done properly, the complete hydraulic sizing simulations are done. So process design, mechanical design, electrical design. So all these systems are designed as per their applicable standards. Then there's a basic process control systems. We call them BPCS. And then BPCS is like automated control of the plant operations. Then there in the same BPCS there are alarms, and uh, on the response to the critical alarms or normal alarms, operators are required to or there to intervene in the operational aspects, and they can remove the upset condition of the plant. Then, if both basic process control system or operator is unable to take corrective action, then there are ESD systems, and ESD system can trip the plant if the plant would be BPCS conditions are not being met or alarm is not attended by the operator, then ESD system can automatically take control. And in between, like even ESD system does not work, alarm is not being attended. So there is one mechanical equipment installed, which is fifth layer of protection. These PSVs and PRVs or rupture discs. These equipment may open and high pressure can be released to the atmosphere or to the flare system or to the burn pit system. Then if this also does not work, then for example, for the tank side, there are the bunds where the in case of any equipment fluid release, that fluid can be accommodated into the dikes or in the drainage system. Along with that, there is a fire and gas detection system. Like if something leak, fire and gas detection system can detect that. Then plant emergency response plan, or where the operators or the plant management would be acting in case of emergency. Last one is a community emergency response, like civil defense, hospitals, district management. Those people can also provide help. So altogether, there are 9 layer of protections, and we are addressing today, which is the fifth layer of protection, which is called PSVs or relief devices. Now, what are pressure relief and flare system? Like the people who are working on the plant, they are aware, and when plant is working normal, no issue. But if there is abnormal situation, you wish to trip the plant or we have to shut down the plant, in that scenario, all the hydrocarbons or chemicals what are being processed by the plant has to be relieved to a safe location so as any kind of fire or abnormal situation can be avoided. So that system where in case of system redundancy, if you have to shut down the plant, where those chemicals or gases or hydrocarbons should go, that goes to relief system. PSV is open to the relief system. Relief system goes to the flare knockout drum, and there is a flare, and you can burn all those chemicals. So that system normally is like a pressure relief and flare system. Here, like as I said earlier, pressure relief system has two components. Number one, PSVs. If high pressure is there, PSVs can automatically open. But in case we are activating normal ESD system, so in that scenario, as we will be like a ESD button would be pressed, then all the ESD valves will close, like incoming fluid will close, and the BD valve will open to the flare, relief system, and relief system will be linked to the flare system. So flare system is like whatever fluids are being released, if they are hydrocarbons, they can be burnt. So the relief system sometimes could be open to atmosphere if it is a non-toxic gas like a steam or water. But if it is a hydrocarbon or any toxic, then it has to be like a link to the flare system. It can be burnt. And flare system is a knockout drum and a one like a chimney where or the burn pit where these chemicals or hydrocarbon can be burnt safely. So why we need them? First of all, as we said, there are a 9 layer of protections in general. So relief system is one of the basically protective system. So where overpressure protection can be managed by the PSVs, Then, like if PSV does not protect, then there could be a explosion or leakage or rupture, which can affect the equipment as well as the people or the safety and environment as well. Then, same management of process upsets, separation of liquid, flashback protection is also one part as we need these flare systems. The components wise, if you see here, for example, these are the PSVs, which in case of high pressure will open. This is the main header of the flare or relief system. Then there are the BDVs, we have blow down valves, and these are opened by with the help of ESD system. And then this fluid all goes to a flare knockout drum and you can burn it. So these are the system like components of any relief system and flare system. This part is a relief system and this part is called flare system. Then, like what are the pressure relieving devices? There are various kind of PSVs or rupture discs which are used. Generally, if I have to say, there are like four type. Number one, like conventional PSVs. Then there are like balance bellows type PSVs or PRVs, and then there are pilot operated, and then there are basically rupture discs. But here, if we say pressure relief valves, safety valve, which is also process safety valve, relief valve, or is also pressure safety, pressure relief valve, pressure safety valve, then safety relief valve, conventional safety relief valve, balance safety valve, normally is called balance bellows, then pilot operated pressure relief valves, then pressure and or vacuum vent valves, rupture disc devices. If we see one by one, like this is the pressure relief valve. Like here is the inlet, there is the outlet. If there is a high pressure, this disc will press this pressure spring and it will open at a certain set pressure. Similarly, if you see other one safety valve, similar here, there is a pressure and this pressure would be opening this disc to the upper side and then fluid will go to the outlet side here. Relief valve also similar, and safety relief valve also, if you see, there's no major difference. There is a inlet, there is a this disc. When disc is pushed up, fluid will go this side. Same is the case here. Then conventional safety relief valve means like again, being repeated. Like here, this is the inlet, this is the disc. This will press this spring where the set point. Then this goes up and fluid goes out. And this is a balance bellows. For example, here if you see, balance bellows are used when there is a back pressure of the system to balance inlet pressure and back pressure, which is coming from the relief system. If the high differentiation is there, then balance bellows type safety relief valves are used. Then here, pilot operated pressure relief valve, this is the pilot. And here if you see pilot tube and other like a tube from there, as the differential pressure cross, then this pilot will help this disc to move up and fluid will go out here. Similarly, these are the vacuum or the pressure vent valves where it is a two-way it works. A high pressure, it goes up, and low pressure, the air or the gas can come inside also. Then a rupture disc, it is just like one what you call plate, and if pressure goes more than certain limit, it bursts. So this cannot reset. So in case of the rupture disc, we have to replace once it is ruptured. So if on the process plant, like how the P&IDs, PSVs look like here, like these are the PSVs inlet, but in isometric, actually, it would be seen differently. On the P&ID, it can be shown this way. Another like a diagram in the horizontal vessel, if you want to see it. PSVs are shown this way with the PSV number, the set point, inlet, outlet size, and so on. So we normally relief system below down study report. There's a one content. This study report is done like what are the fluids, what are the scenarios where the system can be overpressurized, where the pressure would be relieved, and then what size of the PSV size should be there, what kind of PSV should be there, type point of view, inlet size, outlet size, material of construction, and then what kind of relief header, what kind of knockout drum, then what kind of layer system. So all this, a complete study is carried out. And since we are covering only PSV part, the PSV sizing or blowdown valve sizing is one part which is part of today's scope. Here, if you see that what is generally covered, the terminology, references, bases and assumptions, then vent system, PSVs, then blow down valves and release, results and discussions, conclusions. Then there is a summary of the PSVs and flare system and so on and so. So this way, this study is summarized. Now, just to check, like I am just speaking. So if whatever I explained up to now, if any message is conveyed to you, so just check, be alert, write your answer into the question answer window. Question is, what is the main difference between pressure safety valve and pressure relief valve? I explained. What is the main difference, or what is the main use, you may say, for the PSV and pressure relief valve? The first option is PSV is used for gas and steam services, where PRV is used for liquid services like oil and water. PSV open suddenly and fully, PRV open gradually. This could be right also. PSV set pressure typically 3% above working pressure. PRV set pressure typically 10% above working pressure, all above. So what is the answer? To me, yeah, many answers are right. Yes, the answer is D, all above. Like PRVs and PSVs. PSVs are used for gas service. PRVs are used for liquid service. PSV open suddenly, whereas PRV open gradually. PSV set pressure generally 3% and above, could be 10% also. There is a discussion. And generally PRV is at 10% above working pressure. So now, which of the following valve type is not a PSV? Which of the following is not a type of PSV? Not. There is answer. Not yes. The balance safety relief valve. B. Pilot operated pressure relief valve. The rupture disc device. Electrical actuated valve. Which one? The answer again is mostly true. Is D. Electric actuated valves are not part of the PSV valve, because PSVs are mechanically operated valves at set point basis. Now, next thing, like normally in every our webinar, so what are the applicable standards and regulations for the PSVs? So one thing I am very glad to see today, even there's a war situation in Middle East, our attendance is quite good. So 270 people are attending this webinar. So it means we are standing up to our mark, and everybody is stable and not afraid of the situation, and going with the normal business of the life. So the standards like API RP 521 comes first. Even though API RP 520 series wise 520 comes first, but in PSVs 521 is first, because that establishes the basis for the sizing of the PSVs, like how much fluid is expected to be released. Then API ST 520, where the sizing and installation guideline for the PSVs. And API ST standard 526. And this one is basically a specification for purchase of the new standard, new PSVs. Whereas API ST 527 is a seat tightness of the pressure relief valve, how it should be managed. Whereas API RP 576 is generally for the operation phase, inspection and maintenance of the pressure relief devices. So these are the basically 5 standards. If I just for the sake, you can get through the as example familiarization. Guide for pressure relieving and depressurization system. So this covers all the basic requirement of the PSV sizing. For example, here if you see determination of the individual relieving rates, principal source of overpressure, effects of pressure temperature composition, effects of operator response, closed outlet, cooling or reflex failure, And then if you see selection of the disposable system like a relief and flare system, then disposal system like a relief systems or the burn pits, and then bibliography and other guidelines are there. This is the API 521. If we go next, that is the API 520, sizing, selection, and installation of pressure relieving devices in refineries, sizing and selection part 1, and then installations part 2. So the API 520 got 2 parts. Then this is the standard specification for flanged steel pressure relief valves. If you see it, its contents, like a general scope, design, then material, inspection and shop tests, then identification and preparation of the shipments and other guidelines. So this is the standard which is used for the selection and size, for the purchase specification of the PSVs. Then this is also a seat tightness pressure relief valves, and it covers mostly, if you see it, here testing with air, mostly how the a valve can be tested with steam, testing with water, testing with air and other method. So this is the how the PSVs could be tested. Then inspection of pressure relief devices, which is the last standard, and this standard covers, like here if you see that, general dimensional characteristics, operational characteristics, and pressure relieving devices general, what types are there, cause of improper performance, causes of improper performance, very important for the operation phase, like corrosion, damaged seating surface, failed spring, plugging and sticking, and others, right? So inspection and testing, how it should be done, like reasons for inspection and testing, shop installation and overall, and record report documentation is also covered. So this document covered how the PSVs should be inspected. So the testing procedure is given in API 527. So if we I already explained what is the difference, but if we have to just for the sake of a more awareness, what is the difference in API 521 and API 520? So 520 should be sizing and installation of the relief devices, whereas 521 is scenario analysis and calculation of the relief loads. Then main output PSV specification sheet or fish size, valve type and material, whereas relief load summary, mass, volume, flow, temperature and pressure. Then typical user, mechanical or piping engineers, process or safety engineers. Then individual devices and its immediate piping, entire relief system including headers, knockout drums and flares. 521 determine what you must relieve, scenario or the loads. 520 determine how to relieve it, device sizing and installation. This is a very important, we should remember this difference between API 520 and 521. Here, part 1 is a sizing, part 2 is installation. I explained earlier, like a guideline how the PSV should be sized, and part 2 is how the PSV should be selected and installed. Then in 521, there is a scenario identification, load calculations, and disposal system. Like a scenario identification means whether outlet blocked, whether there could be a fire, there could be cooling water failure, there could be utility failure, and so on. Whereas like a load calculation mean how much a volume of fluid would be coming out, and then how this fluid would be handled by a relief system, what should be the type of the relief system, the header sizing, the knockout drum sizing, and flare sizing itself also. Then API 521, number 1, if you see that, determine worst case is 521, to take that flow rate and determine the physical size, like orifice and type of pressure safety valve is covered under API 520 standard. These guides explain the principle behind 520 or pressure relief devices sizing, and API 521 for scenario analysis and relief load calculations. Now, so what are the minimum relief system content? As such, if you see, this is just repetition, so as you can get more information. Relief scenario analysis, like initiating events, intermediate consequences, then Relieving rate calculations, for example, design basis, relieving load, wet surface area, relief device selection and sizing. Whereas relief device selection and sizing, device specification, sizing results, orifice sizing calculations. Then disposable system and flare header design, network simulation, hydraulic and back pressure, component sizing. Then system documentation and schematics, which are called P&IDs, PFDs, then other schematics, schematic diagram, simultaneous simulation data, maintenance records also kept in the system. Now, one more question again. Which standard used for sizing and selection of PSVs and PRVs? Which API standard used for sizing and selection of the PSVs and PRVs? Mostly answer is right. A, 520. So what is the difference between API 526 and API 576? So I explained earlier, the API 526 is standard for specification, like how to purchase and manufacturing, what kind of guideline the manufacturer of PSVs would be using. Whereas API 576 is for the operators, for inspection and maintenance team, like how the PSV should be managed once installed in the field. Here, there is a comparison, like API 526, standard for purchase and specification of PSVs and PRVs, define dimension and materials for buying new valves, manufacturing and procurement engineers, this is for the users, and then timing wise before and during production and purchase process. Whereas API RP 576, this RP describes the inspection and repair practice for PSVs and PRVs, guide the inspection and repair of existing valves. Plant inspectors and maintenance personnel use this during the operational life of the equipment or the valves. Then, if you see here, life site, in the initial phase, we specify and buy, installed and commission. Up to this, like this is separate, but specify and buy API 526. Install, commission API 520. Then operate in service, inspect, repair API 76. So this is the flow of the information, how these standards work together. If you start 520, 521, then 526, then 576. This way, the systems are correlated with each other, or the standards are correlated with each other. Now, if you see, generally, like use when selecting, purchasing new PSV, this is when we use API 576. Ensure vendor and vendor valves, vendor of the valves are basically dimensionally interchangeable. Like all valves are standard, like one manufacturer, other manufacturer, they should be compatible with each other with respect to the diameter of the phalanges, inlet outlet sizes, like BCDs of the bolts. So as a one valve, when putting other flange, it can be installed. Then streamlines spares strategy via standardization or fish letters. These are the general requirement. The API 526 is established so as all manufacturer manufacture the valve with the same criteria, so as interchangeability of the spares can take place, or they could be fitted on other piping systems where the flanges would be coming from the other manufacturers. Here, like whereas API 576, inspection procedures are important, testing procedures are being prepared, guidance being provided, then failure analysis and exclusions, like how a valve can fail, what are the causes of the failure, and how those failures could be minimized, what kind of inspection regime should be there, what should be the PSV's testing interval, and pre-pop testing procedures, and so on. So all those areas are covered under this standard. Now, one more question, like what do API 526 and API 576 covers? Just to, these questions are added so as we can have some interactive discussion. Otherwise, I will be speaking and less participation from the attendees. So for that reason, this question is there. So mostly right, but some answer is wrong is also coming. So like here, API 526 fire case design, storage tank design. B, control valve sizing, relief flow calculation, overpressure analysis, chemical compatibility, but we know the standard API 526 is a standard for purchase specification of PSVs and PRVs, whereas API 576 describes the inspection and repair practices for PSVs and PRVs. Answer is D. So just to keep you like an interactive discussion, at the end we'll also give you a platform to ask live questions. So, but we added few questions in between so as you are not sleeping and I'm not getting you bored. Now, how the basis for PSV sizing can be established in accordance with API 521, just basis of selection. So as you can think, how process engineers are establishing this basis for the selection of the sizing of the PSVs. Here, like there are various scenarios. For example, if a fluid is going into the in the process plant and outlet is blocked, where there could be an inadvertent closure of the valve or opening of the valve, check valve malfunction, utility failure, partial failure, electrical mechanical failure, loss of fans, loss of heat in a series fractionation system, loss of instrument air and electrical power, reflux failure, abnormal heat input from reboiler, heat exchanger tube failure, transient pressure surges, plant fires, process changes, chemical reactions. Now, if I try to explain, for example, what is the effect if outlet is blocked? If outlet is blocked and fluid is being compressed, being pushed by, let's say, not centrifugal, reciprocating compressor. So it means the reciprocating compressor will keep increasing the pressure and there could be a downward system, could be overpressurized and may rupture. So other cases, if like the centrifugal compressor and if it is pressing the fluid to compressing the fluid to be transmitted to second place, so in this scenario, there is a maximum pressure which a centrifugal compressor, centrifugal pump can generate maximum pressure. However, the reciprocating or positive displacement machines, whether pump or compressor, they will keep increasing the fluid till your fluid got some exit point. So it means if outlet is blocked from any system, outlet like there's a pump or there's a compressor in between, the piping, some equipment, some exchanger, and then there's a valve. If that valve is closed due to some reason, in that scenario, the fluid has to go out somewhere. So you need to put a PSV to provide that path. And that PSV sizing would be done on the assumption of the outlet blocked. For example, if there is a heat exchanger which is cooling the fluid, a reflex which is coming on the top of the column of the fractionation tower. So in that scenario, if cooler heat exchanger is not working, it will not provide enough cooling for a cooling tower or air fin cooler or cooling water-based heat exchanger or air fin exchanger based on the air. If that is not working, it means there would be less condensation. A less condensation means there would be high volume of vapor, and that high volume of vapor will create some kind of basically high pressure in the system. So if system will not have capacity to absorb that high pressure, there should be PSV. So in this way, like the sizing basis of the PSVs is selected, whether what could be the scenario, how this high pressure would be generated, and for relief of that high pressure, what flow rate we need to exit through the PSV. This is the API 521 basic requirement. Like common scenarios I already explained, like a blocked outlet, external fire, heat exchanger tube failure, control valve failure, utility failure. There could be any scenarios. So I only explained two. Then all these scenarios are also discussed during HAZOP or LOPA analysis. Like if we have the right protections provided to avoid if system will not have a high pressure. So in those scenarios, if high pressure comes, then what kind of layer of protection we are providing? Whether it would be ESD system, and along with the ESD system, there would also be PSV, PRV, or along with ESD system, maybe BTV system. So all these systems are selected based on HAZOP and as per API 521 guidelines. So then, like we said, fire case. For example, if there's a fire outside, fire which is a negative scenario, if fire comes, then inshallah things are gone and you're out of control. Let's say thermal expansion. And like if a system from winter to summer, we scenario, take a scenario. If there's a high temperature, like summer in desert, like it could be 80 degrees Celsius or 50 degrees Celsius, 70 degrees Celsius on the metal temperature. So if there is a liquid inside and no outlet opened, in that scenario, the liquid may convert into vapor, and that vapor will overpressurize the system. If system is overpressurized, system can burst, a pressure vessel can burst. In that scenario, we need to provide thermal expansion relief valve. In case if there's a fire outside, how much fluid would be there? What is the wet service area? Then accordingly, we have to calculate the volume of the fluid which will be going out. So in this scenario, we need to determine what is the fluid, whether liquid or gas, what is the molecular weight, what are the effect of the heat on this particular fluid, and then accordingly, like whether there will be single PSV, double PSV, what kind of exposure time, and what kind of overpressure we need to consider. Here, first is establish relief rate, controlling case, whether outlet block, fire scenario, heat exchanger failure, or any other failure which may overpressurize the system. Then determine relieving pressure and accumulation. The single PSV operation, 10% accumulation, which is 1.1% of the set pressure. Then fire exposure, 21% accumulation is allowed, 1.21 of the set pressure. Then multiple devices, 16% accumulation, it means the 1.16 of the set pressure. These are when we are selecting the overpressure and what volume is required to be accumulated in the fluid, because we don't want PSV should be abruptly lifting now and then, because this would be like a PSV lifting is called abnormality in the plant, and if it happens, it may lead to the shutdown of the plant, and shutting down of the plant is not likely like a favorable scenario for the operator. So we need to minimize it. And we put all the actions like a PSV should not be lifting. Like normally PSV average lifting scenario or time between the PSV lifting is 5 to 10 years, one time. This is normal. So here, then we have to select the PSV type, whether conventional type, balanced bellow type, or then orifice selection and the size of the PSV also. Then whatever process we are following, as per API 520 and 521, complete documentation is required to be selected and registered. Now, if I go through one example for PSV sizing for outlet blocked volume release calculation one. So just to make you familiar how the PSV sizing is done. So here, when we are using API 520, determine the relief requirement, API effective area and effective coefficient of discharge, back pressure coming from the relief system, cold differential test pressure, relieving pressure, sizing of the gas or vapor relief, sizing for the steam relief. Well, there are various scenarios. Sizing for the liquid relief, then sizing of the liquid relief, pressure relief valves not requiring capacity certification, sizing of the two-phase liquid flow, sizing for the rupture disk. So here, if you see, before sizing, what is important, relieving pressure, cold differential test pressure, back pressure, API effective area and effective coefficient and discharge, then there are various scenarios which are applicable. Then once we're done PSVs, there would be orifice area calculations, and this orifice area calculation have a designation like a orifice designation, and then with this designation we select the sizing of the PSV like a 2-inch size, 2x3, 4x6, 6x8, 8x10, 10x12, like a 10-inch by inlet and 12-inch the outlet, like a largest P&ID or a bigger size P&ID, you can say. Here, if we take a block outlet scenario that I explained, practical example, like if the outlet is closed by valve or some other reason. Scenario, a separated vessel, separate oil and water. The water outlet line is blocked by human error, closed valve. The feed pump continued to run, leading to a blocked outlet case. Calculate the required PSV orifice area to handle the block flow. This is the calculation. Here, how we do, what are the formulas there? Maximum feed flow rate, Q, let's say 100 cubic meter per hour. Fluid water density is 1000 kg per meter cube. Maximal overworking pressure, 10 bar, let's assume. This would be actual, we are assuming a scenario. Set pressure also 10 bar. Then overpressure means 10% mean 1.1, 11 bar. Living pressure would be 11 plus 1.013 atmospheric, 12.03 bar A. Back pressure 1 bar assumed negligible. Viscosity 1 cp. Then determining the relief capacity, W is equal to Q into P, the formula is applied. Then calculation of the required orifice area, this is the equation, and these are the variables, and a dimensional consistency is required to be followed. Then after the conversion, this is the normal, like conversion, the US rate will QL is equal to 440.3 GPM, so as all are in the 1 unit dimension. Here calculation is applied, and then we got the orifice area 1.477 inch square. Then selected standard PSV size from the API 526 standard orifice sizes. J orifice 1.287 and K orifice 1.83. We cannot take smaller one, too small. Then we have to take the next size, which is 1.838 inch square. And this is 3 by 4, 3 inch inlet, 4 inch outlet. This is the PSV sizing done. This way, PSV sizing and selection is done. Then all PSVs are sized this way, and the record is kept. So this is a report is prepared like a PSV sizing calculation package 1. There's a sample basically prepared for you. So as you know, each PSV is calculated, and then the record is kept in this report as such. Then key consideration for the blocked outlet, for example, whether it is a gas vapor system, right? This is the one. Then there could be a thermal relief, compressor blocked outlet, or two-phase flow outlet. So there are various scenarios which are required to be considered. Like if a gas vapor system block or thermal relief, which I gave you example earlier, then compressor blocked outlet means relief rate is based on the compressor capacity at the maximum speed and relief pressure. Two-phase flow, if the blocked liquid phase flashes, a two-phase calculation typically 2 into 10 multiplied by the larger area is required generally. So this is a scenario how the outlet block capacity is being estimated. So one more questions. So as I'm not like leaving you aside, the question is, according to API 521, which are the steps in establishing the PSV sizing? What are the steps to be followed in establishing the PSV sizing? Number 1, identify scenario. B, define the system, clearly define the protected system and understand its operation. Then C, establish worst case, determine the credible worst case scenario that produce the maximum relief load, which will dictate the necessary orifice size. Then D, documentation. Document all identified scenarios and the resulting reasoning behind them to justify the design, often utilizing guidance from API 521. The answer is mostly filled by you is right, is E, all of them. This question is formulated so as it will help us to remember what are the 4 steps in establishing PSV sizing basis. Now we go to the operation side of the PSVs, and just to have some familiarization, what are general issues, concerns, and problems faced due to failure of PSVs. Here, there could be a PSV does not lift at high pressure. There could be a catastrophic risk. There could be hazardous release. There could be a cascading equipment failure. For example, pressure exceed maximum allowed working pressure, vessel rupture or explosion, fire and potential loss of life. Hazardous release means there could be a toxic or flammable chemical, environmental contamination, regulatory and legal consequences. Then cascading equipment failures, equipment flammable chemical discharge, which can have an impact. Environmental contamination can have a double impact. Then there could be a penalty from the regulatory authority. So PSV failed to open, last line of defense lost. For example, if PSV failed to open, in case of high pressure, this PSV would not be there to protect the system. Then operational issues. For example, if PSV is not working properly, there could be product and economical loss. For example, if there PSV is leakage, fluid would be lost. If it could also lead to a high value of product waste. Unplanned shutdown, a PSV is like First of all, what are the failure mode if I may bring into? The PSV generally have 3-4 problems. Number one, it may lift it at the given set point. This is the PSV purpose. PSV is there, it should pop up if pressure goes more than a certain limit. This one. However, what happens if PSV lift prematurely? It means it will cause the shutdown of the plant because PSV is lifted when it should not be lifting. Secondly, what can happen? PSV is leaking. It means you are wasting the product to the flare line. Third, what could be the case? PSV is stuck, not opening. It means PSV is not opening and the pressure is going high and then it may rupture. So we have to see consequences in the same angle. If PSV is prematurely popping, product wastage. If PSV is not lifting at set pressure, there could be explosion, there could be a rupture. If PSV is lifting at set point, this is the main purpose of the PSVs, and PSV may also leak. Right, sir? So these are the scenarios where we see that product and economical loss, unplanned shutdown, system inefficiency, it may cause contamination as well. Then here, damage to valve and piping system. So how the PSV may have a problem? It could be a chattering and vibration, like a rapid opening closing, severe vibration, damage to seat and disc and connected piping. There could be a problem. Seat damage, debris or the lodge between the sealing surface causes leakage or the failure to open. Then there could be a corrosion and material degradation in the valve due to process. Corrosion fluid damage, stem, spring, and body lead to sticking or premature failure. Then broken spring due to fatigue or corrosion failure, where the spring of the PSV could fail or stuck. Then valve cannot maintain proper set pressure. Like common failure causes and scenarios, like number one, for example, valve is too small, cannot relieve required capacity, system pressure continues to rise above after operating. Number two, if the fluid surface is not correct, debris accumulation, solid formation, then prevent proper pressure relief. Then over tightening connections, poor outlet piping support, incorrect orientation, not vertical, then there could be a wrong spring installed, failure to recalibrate, then reassembly error causing sticking or the wrong set pressure. So there are various scenarios where PSV, these are APA 576 guideline, if there could be a problem in the PSV. The most PSV failures are preventable through proper design, installation, and maintenance practices. That's why many PSVs are installed and working all over the globe. Now, summary of the consequences, like issue, catastrophic failure, failed to open, stuck. Explosion, fire, fatality, that can happen. Unplanned downtime, persistent leakage, high maintenance and repair cost. Then environmental hazard, leakage of the hazardous fluid, safety violation, environmental damage. Then there could be a chattering vibration, equipment damage, pipe damage, ruined seat, and system problems. Here, the main causes basically of the improper performance is a corrosion, falling deposition of the process medium, damaged seating surface, failed spring, improper setting and adjustment, plugging and sticking, misapplication of materials, improper location, history or identification, rough handling of the valve during maintenance, improper differential between operating and set pressure, excessive built up back pressure. There could be other scenario. So here, what we are saying that like the same, how it look like when there are failures. For example, corrosion, this is the impact. Damaged seating surfaces, you can see here, and this valve will not be able to operate at the given time. And you can see all these springs are corroded due to the fluid service. Rough handling, if the valves are thrown on the like a ground without proper like a support or proper manner. Now, failure history of the PSVs and PRVs, so there are big history. These PSVs can fail if it would not be, or if they would not be handled properly. Here, what field data typically show? Mostly, inspection rejections often relate to the seat leakage corrosion and debris buildup. This is the main problem. Then high pressure corrosive service can accelerate degradation and the premature failure. Then observed life varies widely. Some fall in less than 5 years, other may cross 12 to 15 years minimum. Performance depend on basically on process media, installation quality, and testing discipline. So why this matter? PSV, PRV are the last line of defense against overpressure events. Hidden degradation increase risk between inspection intervals. Digital tracking enables target setting, repair, and replacements. So takeaways: data-driven PSVMS, data-driven PSVMS system, PSV management system help detect degradation early and align maintenance intervals with actual risk. So here, like if we just failure mode analysis point of view, most failure fall into two categories: fail to open, like on demand. For example, PSV stuck but is unable to open. The reason we already discussed: corrosion, there could be spring damage, or there could be a sticking like a mechanism due to corrosive or long inactivity, because PSVs are not basically lifting every day. The leakage, if this is debris, damage, wear, erosion from the high velocity fluids, set point differentials. So operational signal leakage often shows up first. Demand failure may remain hidden until the moment of need. This is very clear. That's why PSVs are required to be managed properly. Now, factors point of view, which are important in this kind of things: process fluid properties should be properly studied. Improper sizing installation sizing and should be done in accordance with 52521. Lack of periodic testing, like all the PSV should be tested as per the applicable testing plan, and it should be studied like if the PSV is material construction is suitable for the service. Now, in general data, initial failure to operate probably the proof test data, like a normal failure rate is 1 to 1.6%, but mostly greater than or up to 80%. Share of inspection rejection because of leakage, sticking, and corrosion. Mostly PSVs are like rejected due to leakage, and the sticky or the PSVs are like due to non-operation stuck situation, and it's not operating at the given set pressure. Then 18 PSVs out of 5,810 example finding internal leakage identified in the inspected PRVs. PSVs were found internally leaking, right? So normal life extension expectancy is a 5 to like 25 years they can work. Then initial failure probability, brief of like when we say studies on PRV proof test data show an initial failure to open probability of the approximately 1 to 1.6%, and this is like a pre-pop testing. Then there is a acoustic detection, material selection. These aspects may minimize these problems. Like we do pre-pop testing at proper interval, or installing acoustic sensor can detect valve seat leakage. If valve is leaking, then appropriate material construction, there is a Korean engineer job at a project stage. Now, again, one more question to make you people more interactive. The question is, how do organization manage PRV failure? The question is by replacing valve every month. B, by following a formal PSVMS and RBI program to determine inspection interval, ignore small failures, reduce vessel pressure manually. So answer mostly right. B, by following a formal PSVMS and RBI program to determine inspection intervals. So PSVMS procedure, what it covers: PSV, pressure safety valve management system. Here, purpose, scope, and definition. The purpose is define guideline for design, procurement, installation, operation, and maintenance of the PSVs. Scope also same. Define the valve life cycle, for example, from purchase to disposal, and include type, all like conventional, bellows, pilot operated, all type of the valve. Definition, standardization terms such as set pressure, cold differential test pressure, blow down, and seat tightness. Responsibilities and personal competencies are also covered under this document. define roles, for example, asset integrity, maintenance, and operations, ensure that technicians are qualified to perform calibration, overhaul, and testing. Then inspection and testing requirement as received, pre-pop test, dismantling and internal inspection, cleaning and refurbishment requirement, setting and calibration requirement, seat tightness test requirements, body leak test requirements. So these all inspection and testing requirements are specified in this particular document. Then preventive maintenance and scheduling. This is also covered under this document. Either time-based or RBI-based or risk-based program is followed. Maintain a master database of valve tags, location, and service history. Now, documentation and record keeping, test certificate, inspection report, digital tracking, all are required to be managed properly. Then safety procedure, adhere to job safety analysis, then mandatory use of personal protective equipment while testing the PSVs or removing the PSVs from the plant. Then management of change process is also covered under this procedure. Troubleshooting and failure analysis is covered, and guidelines are provided in this document. So this is one sample document where like prepared by Velosi, like how this PSVMS system can work. For example, here purpose, application, abbreviations, like a safety prerequisites, then ARMS policy, then risk assessment policy for the PSVs, then incident investigations, corrosion management, inspection and maintenance management, inspection and test frequency, role and responsibilities. Then accordingly, like here, if you see shop inspection overalls and seat tightness testing, annual audit, time of inspection, and so and so. So this document is a detailed document, 62 pages. So cover all aspects of PSV management as a guideline procedure. So companies do prepare this document for the management of their PSVs. Then this the same PSVMS is also supported by PSVMS software like a VAIL-Plant PSVMS. So here lifecycle management, safety and reliability, compliance and reporting, these aspects are covered by the software. Then centralized database is prepared. Then risk-based inspection program is also there. Compliance and standards are basically managed through this system. Performance monitoring, automated scheduling, reporting and analysis. So these all aspects are covered under basically PSVMS software. Then it may help to enhance safety, increase reliability, cost efficiency, operational continuity, regulatory readiness. Question again, so make you interactive. Like the question is, what is the main purpose of PSVMS procedure? What is the main purpose of PSVMS procedure? To design pipeline. B, to manage the life cycle of PSVs and PRVs, to increase production speed, to monitor electricity uses. So it's a quite simple question. Answer is B. All others are not relevant. So when we find difficulty making a question, we make this kind of question, so you rightly can find the right answer. So if we can, for these question answers, like if you are listening something, some message is being taken by you. Otherwise, everybody sleep or maybe you just attend. The next question. What is included in inspection and testing requirements? What is included in inspection and testing requirement of the PSVs? As a received test, pre-pop. B, dismantling and internal inspection requirement. C, seat tightness and body leak test. So this is the like minimum requirement in the inspection and test requirement. So the answer is mostly some wrong. But here, as a received test is also part of the PSV's inspection and testing requirement. As we find, we should basically, this is a difficult question. It is some confusion is there, I can accept. So as a received test, pre-pop, dismantling and internal inspection is also covered under inspection and testing requirement. C, seat tightness and body leak test are also covered under inspection and testing requirement of the PSVs. The answer is D, all above. All three are the answer. Right. Now, one more question. What does management of change ensure in PSVs? The valve remains suitable for the process after any change. B, valves are painted correctly. C, valve are replaced every month. D, staff take shorter breaks. The answer is A, valves remain suitable for the process after any change. That is the main objective of MOC. Right. Now, last part, which I will just go through, that is like case study risk assessment of PSVs using FMEC approach and by using our VAIL-Plant PSVMS module. So, like I have spent more time in the previous case. In the case study, it's just a demonstration what we have done. So it will be covered fast. I know it's a fasting month, and in some areas, like I could see that, like in Malaysia, it was just a fasting time, and yes, time-wise, Far East could be a fasting time, but Middle East and Pakistan or India, or the fasting time is little away. Fast breaking time. Sorry. Here, project scope, which was given to us, risk assessment of PSVs is to be completed in order to determine inspection and testing interval. Complete assessment of PSVs consists of two parts: pressure containing function, leakage due to corrosion, pressure relief function failed to open. PSVs are used here under the scope included all spring-loaded safety valves of the conventional balance bellows and pilot operated design, capable of having their set point verified by online or bench testing. As per the basically 592 PSVs at field A, 538 PSVs for field B. This is the total number of PSVs. Following are deliverable for risk analysis of the PSVs at both fields: risk assessment report, PSVs risk analysis, safety valve visual on-stream inspection checklist, detailed inspection and calibration plan, and then VAIL-Plant PSVMS module implementation and training for pressure safety valve integrity management. So these are the standards what were applicable in the project. ASME, for the ASME 8 mainly, then API 520, API 521, 576, sorry, 26 and 527, API 576, 581, and ISO 14224, and SA JA 1011 for RCM or FMECA process. Then BSEN 60812 is the FMEC analysis, and then BS 4778 availability, reliability, and maintainability terms. A guide for RCM standard was JA 1012, and International Standard Application Guidance RCM, and ORIDA for the reliability data. So here, what data we collected, like the steps wise data collection as register development, if you see, functional analysis, functional failure analysis, failure mode identification, failure effect identification, failure cause and maintainable items identification, failure criticality and risk of failure, criticality assessment findings, inspection strategies, and inspection plans. These are the basically general steps. Same steps are shown here. Define the system boundary, gather data and description, define system function, select functional component, and then accordingly component critical, not critical, and so on, the process is followed. Initial review, like a POF assessment, failure history review, generic failure, failure history data analysis, then failure rate estimation, calculate likelihood of failure. And then similarly, CUF estimated functional failure identification, failure mode identification, failure cause and maintainable item, and the CUF goes there, estimate consequence of the failure, and then by multiple of PUF and CUF, we calculate the risk, and then inspection strategies develop. So data, what is required generally for this analysis, the P&IDs, PFDs, PSVs engineering specification and data sheets, PSVs inspection and maintenance report and task list, PSV asset list, PSV failure history, vendor catalogs, operating and process manuals. Here, the total number of PSVs is a breakdown. So the PSVs, for example, like system-wise, total 592. This is 538 for the field B. Then here, as a register loading criteria, like pressure, temperature, inlet, outlet size, design type, list of PSVs. So all are basically considered in the assessment. And here the data like as register, which is imported into the software, which cover the PSVs, and they're all basically engineering data, operating data, manufacturer data, and their associated information. Here This is like the opening screen of the log screen of VAIL-Plant, like PSVMS module. So we use the system to conduct FMECA, and it covers both generic and operator reliability data, generate PMR, generate customized reports also. So like here we provided them PEMS, PIMS onshore, PSVMS, and wellhead management system, and ISMS. So these modules were provided to this client. So here the basically we call it dashboard of the PSVs, where we calculate the reliability aspect, risk assessment, the inspection interval, and overhauling aspects as well. And there is the hierarchy of the plant, and you can go to each PSV, you can search also. Here, the general data of the PSVs, or you can see in the form of the form. It could be list view, is the form view. Then here is the hierarchy of the PSVs, which you can go to each area and you can reach to the actual PSV tag. Then here functional performance standard for PSVs are mentioned as below. The pop up at preset pressure set point to release defined amount of fluids as per engineering specification, to reset without seat leakage when pressure is below the set point. These are the normal functional performance standards. Then normal possible functional failure is considered as a loss of the function of the PSV. Function to pop up at set pressure, fail to pop up at set pressure. To discharge defined amount of fluid as per a data sheet, fail to discharge defined amount of fluid as per data sheet. To reseat without seat leakage when pressure is below set point, fail to reseat without seat leakage when pressure is below set point. Similarly, pressure safety valve components, or the pressure safety valve and failure mode. There could be various failure mode which could be applicable, like external leakage, fail to close on demand, fail to open on demand, minor in-service problem, structural deficiency. Here, all the failure modes which are applicable in the system, they are defined. Like you can see the failure modes. FMEC analysis would be there again. Probability analysis, consequence analysis would be in the next slides. Here, external leakage, fail to close on demand, fail to open on demand, minor in service problem, structural discontinuity. Structural deficiency basically. So here, these are those failure mode which I show. Here, like when there's a failure mode, there's a failure effect and failure effect description. External leakage, operational process, then fail to close on demand, functional and performance issue, fail to open on demand, operational and process. For example, a PSV, this on fuel gas line failed to open on demand, overpressure will result in damage, rupture of the equipment with the piping, and will lead to fuel gas dispersion in the area, which could lead to injury to the personnel working nearby and economical losses. Similarly, these details are provided against each failure mode and failure effect. So here, if you can see here, there are like a failure cause, failure effect description is there, and then there's also probability of failure and consequence of failure are selected, and risk is basically calculated. Like here, if the same thing is made here, like a failure mode, failure cause, failure effect description, then maintainable item, and then safety risk, business risk, environmental risk, capital risk, and then these are coming based on the probability and consequence data. This is coming next. Like failure mode, causes and improper performance, causes of improper performance, then maintainable items. So here, external leakage, which could be corrosion, damage O-ring, damage tube or tube connector, damage pilot assembly, or cause internal or external leakage when the valve is in service. Pilot assembly, tube and tube connector, gasket and casing and O-ring, where these items are required to be maintained. So these information is arranged in our FMECA analysis. Then there is a risk criticality, is the probability of failure and consequence of failure. Probability of failure, consequence of failure mean probability is expressed in terms of frequency of an event that is measured as the ratio of that event to the total number of possible events. The value is a number between 1 to 5. Consequence of failure also same. Or failure is description of the effect and failure event to operation, personnel, or the environment. So here, consequence failure is analyzed: fluid service, clean, dirty, size of the PSV, toxic, whether the PSV is linked with the flare, not linked with the flare. Those aspects are also covered. Then here, the following failure modes, for example, external leakage process, fail to close on demand, in-service problem, all are covered. Here, then this is the risk position of that particular PSV, whether medium or high risk position. Then accordingly, the probability is taken based on the reliability data, MTBF based, and this is the consequence of failure, which is like level 1 or level 2 aspects, right? Then criticality, risk failures, all failure modes, we have assigned PUF, CUF risk, PUF, CUF risk. This is safety, environment, economy, criticality, medium for this particular. The leading one is taken here. So this is the end result where we have the failure mode, failure effect, then consequences, causes, then PUF overall, safety risk, environmental risk, business risk, and capital risk. This is the FMEC analysis of that particular PSV. And this is the end result, what the PUF, CUF, and where we stand. So here, in general, we found that like a total number of PSVs which are found in high risk are 25, medium high 10, medium 519, low risk 38. So high and medium high are between 25 and 10 mean 35. Then this is the distribution of those PSVs, like risk point of view, 419 were coming here. This is the number. Then 335, the various distribution in the risk matrix. Then this is the PSV for the other plant, plant B. So here 50 high, 07 medium high, 530, 354 medium, and low is 127. This is the distribution of those PSVs in the risk matrix. Then three type of inspection required for PSV as per the applicable scenario: visual on-stream inspections, inspection and functional testing, shop inspection overhauling, and shop inspection overhauling would be required if pressure safety valve does not pass the inspection and function test, proposed inspection interval based on criticality and risk, fluid service type. So the strategies, the inspection strategies are defined as per the guideline of APA 576. However, the interval are based on criticality risk of a particular PSV. As there can be some cases where PUF can be higher while criticality can be lower due to lower CUF. Similarly, PUF can be lower while criticality can be higher due to higher CUF. Criticality depends upon many factors which when combined with fluid service lead to the proposed inspection intervals. Here you can see that like equipment categories, like a service, clean or dirty, overall criticality point of view, inspection, functional test, these are the months, shop inspection overall, these are the basically frequency, and visual on-stream inspection, these are the numbers basically, you can see that. For this is the criteria for the determination of the intervals, like 60 months, 48 months, 36 months for the clean service. Then shop inspection overall, 60, 48, 36. Visual inspection on stream, 2 months, 2 months, 2 months. The clean service hydrocarbon gas, hydrocarbon oil, fuel gas. The dirty service is considered crude oil, seawater, and furnace oil. Then below is the main strategy for PSV. We like a 6-109, 1A against each failure mode, like one PSV only. So where we have selected against ELP, FTC, FTO, SCR, STD, a 2 months interval, 36 month interval, 36, 2, and 36. These intervals are taken forward for the applicable activity. And then this is the PMR, like what activities to be done for this PSV on monthly basis or like a 36 monthly basis. This is a 2 monthly basis and 36 monthly basis. So now visual on-stream inspection, like normally what is required to see, perform visual inspection of PSVs to check the leakage and seals. Then as an on-stream visual inspection should be carried out to check the following: upstream and downstream isolation valves, if any, are opened or sealed, seal protecting the spring setting have not been broken, the relief device is not leaking. This may be checked visually. The continuous operation of the heat tracing provision, if any, provide the low temperature application of the valve and discharge piping. Condition of insulation and cladding on the heat trace piping and valve. Then gauges, blinds, if exist or not. Then here functional testing, bend testing, what we normally do, the inlet and outlet shall be examined. It shall be ensured that the correct calibrated test gauge is used. All safety valves shall be tested in accordance with the relevant code to which the protected equipment is designed. After final adjustment of the valve shall be popped at set pressure at least once to prove the accurate setting. PSV test pressure range would be followed. Allowance for the hot setting shall be made as per the manufacturer recommendations. Then shop inspection overhauling, determine, like when we are doing shop inspection overhauling for the PSV, these are general guidelines. Determination of PSV dismantling depends upon the result of as received pop test just conducted. If the PSV pop beyond the tolerance of plus minus 2% PSI of set pressure less than 70 PSI or 3% of the set pressure greater than 70 PSI, then the valve need to be dismantled and reconditioned required. Valve should be carefully dismantled in accordance with the manufacturer manual and recommendation. During dismantling of the valve, check and record the following, like continued on next slide. Record all original ring settings and loading screw position. All ring settings are relative to level position. Movement away from the inlet in plus rather than minus, always like this detail is there anyway. Then the flanges for the evidence of the pitting, roughness or decrease in the width of seating surfaces. The spring for evidence of the corrosion cracking should be checked. The bellows, if applicable, for evidence of corrosion cracking to be checked. The external surface for any indication of the corrosive atmosphere or mechanical damage should be checked. The body wall thickness should be checked. Then valve components and material for match with the information on the identification tag and specification card should be checked. The pilot and associated parts should be checked. So this is a report, what we need to follow. And then this is the basically inspection task list. What are which all the guidelines which I just explained are summarized under these activities line by line. This is called task list, which is part of the SAP or the CMS system as well. Recommendation, I would not like to go for the study and go to the questions. Then we conclude the discussion and we will ask for the question answers because we are already at 3:40. So what is the purpose of preparing pre-retrieval and reinstallation checklist? What is the purpose of preparing pre-retrieval and reinstallation checklist? To delay maintenance, to ensure all maintenance and corrosion steps are properly acknowledged, to complete paperwork, to verify supplier invoices. Mostly right. And answer is B, to ensure all maintenance and corrosion steps are properly acknowledged. One more question. During bench testing of PSVs, which of the following is documented? So during the bench testing of PSV, which of the following is documented? Initial leak pressure, opening pressure, and reseat pressure, valve color and brand, operator name only, weight of the valve. Mostly answer is right filled by the all participants. This is A.
Regarding outlet discharge, connected to system is inside or outside? Like open atmosphere, inside pipeline, both conditions.
See, as per the code requirement, if a hydrocarbon service or toxic, if we make it open to atmosphere, it carries risk for that environment, or there could be a fallout. Like if a liquid drops are coming out, that could be a cause of spray on the plant. So having that complication, PSV PRV's outlet is generally advised to be linked with the relief system, and the relief is linked further with either flare system or burn pit. However, we have seen PSVs also open to atmosphere also available, but that is not ideal situation. So PSVs should be linked with the relief system, and the relief system is further linked with if a gas flare, if a liquid, then a burn pit or some other drainage system. Okay, sir.
Okay, sir. Thanks.
Thank you, Mr. Venkatesh.
Hello. I actually
Yeah.
I have a question, sir, about what are the common recommendations from the PSVMS findings. I understand now most of the PSV is related to inspection and testing.
See here, our main objective is for the PSVs which are being managed in the operation phase, right? So recommendations are also given with the same. Like the recommendations are based on API 576. Like number one, we should have the list of all the PSVs. Number two, we should track if there like a failure history is recorded. Defaulter PSV should be identified. Their causes should be assessed, and then accordingly preventive maintenance or inspection program should be developed. These are the normal learning, and other learning recommendation is mainly PSVs, since they are not in the operating phase, like a PSV is installed and it may not be lifted, it may not be popped any time in its operating life. This is normal scenario for many PSVs. So then these PSV may stick to their current position due to corrosion or so. So the main recommendation is it is important that PSVs are kept operational. So it means the pop-up test, pre-pop-up test are required to be carried out at proper interval based on the applicable criticality. So as PSV are not stuck and not operational at the time of high pressure when we need to use them. This is the main finding and is the main recommendation. So I can read your question. Acoustic detection, can you elaborate on it? See, PSV sometimes leaks and fluid might be wasted to flare and you may not find which PSV is leaking. So acoustic emission is a technique. If any PSV would be leaking, there would be some sound, and that sound can tell you this PSV is leaking. So acoustic emission is a technique to detect if a PSV is leaking. Otherwise, you cannot see which PSV is leaking. And there could be hundreds of PSVs. There might be few PSV leaking, and that would be wasting your product. So this technique is to check which PSV is leaking so as corrective action can be taken.
Assalamu alaikum. Can you hear me? Thank you so much for unmute. Sir, I want to ask, how is PSV back pressure considered during calibration and adjustment?
The back pressure is basically assessed based on the system back pressure. Like if it's a flare system, how much back pressure could be there. And then accordingly, it is basically considered or accounted for in the calculations. Like 1 bar, half bar, or if a system is connected to other pressurized system, then there could be high also. But in general, flare system, maximum back pressure is considered as 1 bar. So this is normal practice.
Thank you so much. Sir, I have another question. Can we consider self-operated flow control valve as a pressure safety valve or not?
No. Basically, PSVs are which are the valves which are covered under API 520 and 521 and also under 526 criteria. So these are the basically mechanical devices which are operated under spring or pilot. They are like PCVs are not called as PSVs. They're part of the control.
So as we can, as we see in petrochemical industry, the PCVs has also a spring-loaded seat and spring-operated function.
Those are considered as a part of control valves, and control valves are covered under API 554. So these PCVs are not considered as a PSVs. So this is as per the industrial practice. And if you have any question in between, you can send by email to us, and we'll be happy to answer. And we look forward to meeting you next webinar, maybe 1 month from now. We wish everybody remain safe and war will end by then. Thank you very much, everyone, and have a good day.